This is lesson 3.1 on the vertex of a parabola. Now previously we've looked at quadratic equations. We looked at how we can solve certain quadratic equations by factoring, certain others we can solve by using the quadratic formula. Now remember, the way we got the quadratic formula is by using the process known as completing the square. We saw completing the square again when we looked at circles, and today we're going to see it yet again when we're talking about the vertices of a parabola. So a quadratic function, so if we have our function equals one of these second degree polynomials, the shape that its graph is going to take is that of a parabola, and vice versa. If we have a parabola, it's described by a quadratic polynomial. We've got three common forms to put our quadratic functions in. We've got our standard form where everything is multiplied out, ax squared plus bx plus c. We have our factored form where we can easily see where the zeros of the function are going to be. So here the factored form is a times x minus x1 times x minus x2. So x1 and x2 are going to be the two zeros for the function. And then finally the vertex form, which is what we're going to focus on today. A times x minus h squared plus k. We'll talk about that more in just a second. But this is a perfect opportunity to tell one of my favorite jokes, because it's both a Bible joke and a math joke. So Jesus was preaching to the crowds once, and he said, "The kingdom of heaven is like y equals ax squared plus bx plus c." And all the disciples were very confused and discussing amongst themselves, what does he mean? What does he mean? And Peter chimes in and says, "Oh, just you guys settle down. It's just Jesus telling one of his parabolas again." Womp womp. Okay, so back to math. The vertex form of a quadratic function. That's what we'll be looking at most today. The way we get our quadratic function into this form is by completing the square. We'll see in just a few moments a couple examples of how to do that. So if our function is in vertex form, this is nice because we can tell two things about this parabola very quickly. First, we can see where the vertex of the parabola is going to be. The vertex of a parabola is the lowest or the highest point on the parabola. It's basically where it turns around. When we're in vertex form, the vertex is going to be at h comma k. Furthermore, if we see what our a value is, if our a is positive, this means that we have an upwards opening parabola. If it's negative, we have a downwards opening parabola. So this is interesting because if a is positive, that means that our vertex, that is the lowest point on our parabola, or another way to state that is the absolute minimum on our parabola. Similarly, if a is negative, so if the parabola is opening down, the vertex is the highest point on the parabola, or the absolute maximum on the parabola. We'll actually use that fact in our application problem for this section. Okay, so let's take a look at this example. Find the vertex of y equals x squared plus 6x plus 12. So if you remember what we did when we were looking at finding the center and radius of a circle when we were completing the square, then we're going to start off the exact same way. So we're going to group together these two x terms. Now our knee-jerk reaction is to factor out an x, since we have that in common here. We do not want to do that, however. If we were to factor out anything, it would be the coefficient of the x squared term. However, since here it's just 1, we do not need to worry about it. So our equation, or our parabola, or our quadratic, is going to be, so let's write x squared plus 6x. I'm going to leave myself some room. I'm going to leave my constant term alone. I'm going to leave it right here. So x squared plus 6x, remember, to complete the square, we're always going to add something in. That thing that we add is going to be half of this number squared. So in this case, we need to add 9. Now remember, when we were completing the square for a circle, whatever we added to one side of the equation, we added to the other side. We can still do that in this case. If you feel better, you can just add 9 to the other side of the equation right here. What I would recommend, however, is leave this side of the equation alone. Leave your y alone, leave your f of x alone, whatever we're saying that our quadratic is equal to. Leave that side alone. Instead, keep things balanced another way. If I've added 9 here, I can keep this side of the equation in balance by turning around and subtracting 9. So if I've added 9 and subtracted 9 from this side, I've really changed nothing. So this is the same equation, this is the same function that it was before. But do not, a early mistake is to say, all right, I have 9 minus 9, those cancel out, so I'm right back to where I began. That's true, but that's also silly. We don't want to do that. So we're going to simplify the 12 minus 9, so that's going to be 3. But don't forget this, the whole point of doing this was so that we can write this as a perfect square. So it's going to be x plus 3, remember it's always half of this number here, squared, plus then 12 minus 9, that will be 3. So I'm now in vertex form. So I know that the vertex of my parabola, this is x minus h, so my h in this case is negative 3. This is plus k. So my k is going to be at positive 3. So there's my vertex, negative 3, comma 3. So we'll go through the same process every single time to find the vertex of a parabola. Notice too, we can tell what direction the parabola is opening, up or down. In this case it's going to be up. See how our implied coefficient here is 1. That's a positive number, so it's going to be opening upwards. Okay, so here's a little bit more difficult one. Find the vertex of y equals 3x squared minus 9x plus 10. So we're going to start off the exact same way as before. We're going to be completing the square. So I want to group together my two terms that have an x in it. So I want to group together my 3x squared term and my minus 9x term. What's different this time, however, is notice that the coefficient of my x squared is 3. So between my squared and linear terms, I want to factor out that 3. So this is 3 times x squared minus 3x. I'm going to leave myself some room. My plus 10 is just chilling right there. So I've factored the 3 out, so 3x squared minus 9x has become x squared minus 3x. I'm going to complete the square in the exact same process as before now. So I need to add in a number right here. It's going to be half of this number squared. So half of negative 3, that's negative 3 halves, squared, that's going to be 9/4. So remember, when we square a fraction, so negative 3 halves in this case, squaring the fraction, we just square the top and the bottom. So we can think of this as negative 3 over 2. So negative 3 squared over 2 squared, that's just going to be 9/4. So that means that I'm adding 9/4 right here. Now to keep everything balanced, just like before, whatever I add in, I need to subtract the corresponding amount to keep this balanced. Notice, however, I haven't really added in 9/4 because everything in these parentheses I'm multiplying by 3. So I've actually added in 3 times 9/4. So we know 3 times 9/4, you can treat 3 as 3 over 1 and multiply straight across. So we have 27 over 4. So this looks like 9/4, but it's really just 27 over 4 in disguise. So to keep everything balanced, I've added it here. I need to subtract it over here. There. Everything is balanced. Everything is all well and good at this point. So I can now factor this part, write it as a perfect square. It's x, and it's always going to be half of this number. So minus 3 halves squared. Now I have 10 minus 27 over 4. 10, if I multiply top and bottom by 4. 10 we can think of as being 10 over 1. That gives me 40 over 4 minus 27 over 4. Let's see here. I think that's going to be 13 over 4. Positive 13 over 4. And so now we are in our vertex form. So the vertex of this parabola, remember it's x minus h squared plus k. So minus h. So my h, the x coordinate of my vertex, is 3/2. The y coordinate is 13/4. And there we go. That's the vertex of our parabola. Right. The number of delicious cookies produced per day by n elves in a hollow tree can be modeled by the function c of n equals 40n minus 2n squared. What is the maximum number of cookies that can be produced, and how many elves are required to make them? So I'm going to do something just a little bit different to start off with. So notice that this function that we're given, we can actually factor it simply. Now we have not needed to factor anything up to this point, but just to illustrate something quickly. So c of n equals 2n times 20 minus n. That's what we get when we pull out a 2n from this. What that tells us is that we can factor, or rather we can figure out what our graph looks like pretty easily. We'll use brown since we're dealing with cookies here. We know that our graph is going to have a 0 at 0 because the whole function will be 0 when this part is 0 or this part is 0. So we have a 0 at 0 and a 0 at 20. Now, a nice fact to remember, the vertex is always going to be right in the middle of our two x-intercepts. So we know that the x value of our vertex is going to be 10. So if we were only asked how many elves do we need, we're done. We need 10 elves. And this kind of makes sense. If we have too many, they're going to eat all the cookies that they make, but if we don't have enough, they're not going to make enough cookies. So 10 is exactly where we need to be. However, the problem asks us not only where do we, or rather how many elves do we need, but what is the maximum amount of cookies. So in this case, you could just plug in 10 for your n value. And that would give us 2 times 10, so 20 times 20 minus 10. So we're done. 200. We need 10 elves to get the maximum, and then 200 cookies. So 10 elves and 200 cookies. Now, suppose that we didn't have a function that was so easily factored. Let's take a look real quick at how we would handle this using our vertex form of a quadratic. So just like our previous examples, this is 40n. 40n, there we go, minus 2n squared. We're going to group together our variable terms. Well, it's a good thing because we don't have any constant terms in this case. So I'm going to write it as negative 2n squared plus 40n. Now notice my coefficient of my squared term is negative 2, so I need to factor that out. When I factor this out, this becomes n squared minus 20n, and I'm going to leave some space because I know I need to add something to complete the square. What do I need to add? It's always going to be half of this number squared, so it's going to be 10 squared, so 100. Now, I haven't actually added 100, it's negative 200. So if I've added negative 200, to keep things balanced, I need to subtract negative 200. But we know that's just adding 200. I'm just being difficult. So this is negative 2 times, all right, this is now a perfect square. That's the whole point of going through this process. So we write it as n minus half of this number, 10 squared, minus negative 200 is plus 200. So our vertex for this graph is going to occur at 10, 200. Well, what does our variable represent in this case? What does our n represent? This is our number of elves. Whatever our variable represents is going to be this number here, and the thing that the function as a whole represents will be our second value. So this is the number of elves, and this is the number of cookies. So once again, we arrive at the same answer. We need 10 elves, and they will make 200 cookies per day. Either one of these is going to work just fine. But let me caution you, if we don't know, if we don't have a function that works out nicely, here we had one that works out nicely. We can factor it easily. We can find where its zeros are pretty quickly. And furthermore, the zeros are nice numbers. We can find what value is smack dab in the middle. That doesn't always work. For a word problem, feel free. Try either approach. Either one is going to work just fine. For our drill problems, however, I think you're going to find that it's going to be a little bit more efficient to go with this approach, to rewrite our quadratic so that it is in vertex form. But for word problems, again, whichever way you're more comfortable with, whichever way makes more sense, have at it.